It's pretty amazing to think that you can measure something fundamental about the entire universe using a couple of simple pieces of metal on a tabletop. Today, that's exactly what we're going to explore. Let's get into it. So, first, let me ask you something. If you needed to get a tiny charged particle, like an electron, to move in a perfectly straight and predictable line, how would you build that perfect highway for it? Well, believe it or not, it's way simpler than you might think. All it really takes are two simple metal plates. Seriously. This elegant little setup is the key to unlocking and controlling the subatomic world. But of course, these aren't just any two pieces of metal. When you set them up correctly, they become a tool for creating something incredibly special, a perfectly uniform electric field, a true superhighway for charges. So what exactly are we talking about when we say parallel plates? Well, it's just what it sounds like. You take two conductive plates, you place them a certain distance apart from each other, and then you hook them up to a voltage source, like a regular old battery. That's pretty much it. Okay, so how do these simple plates create that perfectly uniform field? It's actually a fascinating and surprisingly straightforward process. Let's just walk through the recipe. It's really just 4 easy steps. So 1, you put the plates in position. 2, you connect the battery. Now, as soon as you do that, the battery's voltage starts to work, pulling all the negative charges to one plate and pushing positive charges to the other. And now, here's the really crucial part, step 3. Those charges don't just spread out randomly. They all line up neatly on the inner surfaces because they're attracted to the opposite charges across the gap. And that perfect, neat alignment, step 4, is exactly what creates our beautiful, uniform electric field right in the middle. And this is really the magic of parallel plates. I mean, think about the field from a single point charge. It radiates out in all directions and gets weaker the farther you go. But not here. In between these plates, the field is constant. The strength is the same pretty much everywhere between them. And the best part, we can control this field with amazing precision. Its strength all boils down to just 2 things: how much voltage we're pumping in from the battery and how far apart the plates are. The relationship is just so beautifully simple. E equals V divided by D. E is your electric field strength, V is the voltage, and D is the distance. So if you want a stronger field, just crank up the voltage or nudge the plates a little closer together. It's that direct. All right, so we've built this perfectly controllable electric field. Why is that so useful? Well, for one thing, you can use it as a kind of subatomic slingshot. Because that force is constant and uniform everywhere inside, it gives a charged particle a consistent, powerful push across the entire gap. You're basically taking the stored-up electric potential energy from the plates and converting it directly into kinetic energy, the energy of pure motion. And the amount of acceleration is, well, it's just staggering. Get a load of this number. In a pretty typical setup, a single tiny electron can be accelerated at over 281 times quadrillion meters per second squared. I mean, that is an almost unimaginable amount of force to exert on such a tiny particle. But all this power isn't just for making things go fast. You can also use it for incredibly fine control, which brings us to one of the most clever and elegant experiments in the history of physics. So instead of a slingshot, what if you wanted to do the opposite? What if you could create a force field so perfectly tuned that you could trap a particle, make it levitate, perfectly suspended in mid-air? Well, back in the early 1900s, a physicist named Robert Millikan took this simple parallel plate setup and used it to achieve that exact incredible feat of control. His whole setup was absolutely ingenious. He used an atomizer, like an old-fashioned perfume bottle, to spray a fine mist of tiny oil droplets into the space between the plates. As they were sprayed, these little droplets would pick up a bit of static charge. And then he'd just watch them through a microscope as they started to fall. Now, Millikan knew there were 2 main forces at play here. You've got gravity, obviously, which is pulling the tiny oil drop down. But by applying a voltage to the plates, he could create an electric force pushing up. So the whole trick of the experiment was to carefully adjust the voltage to get that upward electric push to perfectly equal the downward pull of gravity. And when he got it just right, the oil drop would just stop and hang there, motionless, suspended in the air. This perfect little balancing act was the whole key, because by measuring everything in his setup when that drop was floating, Millikan was able to unlock one of the most fundamental secrets of our universe. Now, to do this, he had to make a few really brilliant assumptions. He figured, okay, all electrons are probably identical. Their mass is so tiny we can basically ignore it. And here's the big one. He theorized that the total charge on any single oil drop had to be a whole number multiple of the charge of one single electron. In other words, a drop could have 2 or 3 or 10 extra electrons on it, but it could never, ever have 2.5. Charge comes in packets.
So after doing this experiment over and over and over again, meticulously measuring the mass of the drops and the exact voltage needed to suspend them, he calculated the charge of one of those fundamental packets, the charge of a single electron. And in 1913, his result was 1.69 times 10 to the minus 19 coulombs.
So, how good was that measurement made over 100 years ago? Well, the value we accept today, using technology that Millikan couldn't even dream of, is 1.60 times 10 to the minus 19 coulombs. That is just stunningly, remarkably close. Think about that. He measured a fundamental constant of the entire universe using a tabletop experiment with some oil drops, a battery, and a microscope. Just incredible.
It really makes you wonder, doesn't it? What other profound secrets are out there, just waiting for someone with a simple, elegant experiment and a clever idea to come along and reveal them?